Good afternoon, everyone, and thank you all for joining this year's Mildred Dresselhaus Lecture. It's great to be able to all get together to remember Professor Dresselhaus while celebrating the great accomplishments of this year's speaker, Professor Jelena Vučković from Stanford University. As we all get together today, it's with heavy heart that we have heard about the passing of Dr. Jean Dresselhaus, a renowned physicist, as well as Millie's longtime companion, late September. On behalf of everyone here at MIT, I would like to send our condolences to Millie and Jean's family, friends, and colleagues, and we would like to dedicate today's session to both Millie and Jean. With that, I would like to invite Professor Jensen Huang, Professor of Electrical Engineering and Computer Science here at MIT, and a longtime friend and collaborator to Millie and Jean, to open our session with some opening remarks.
Good afternoon, everyone. Welcome to the 2021 Dresselhaus Lecture. This lecture is set up in honor of our dear Professor Mildred Dresselhaus to recognize a colleague in science and engineering with whose leadership and significant impact echo Millie's life, accomplishment, and values. Millie was a giant with her tremendous contributions to science and technology. She had set up a great example for all of us to follow. This year, we also highlight Millie's lifelong companion, Jean Dresselhaus, who was a brilliant physicist that will be remembered for his pioneering idea that shaped the modern band theory, particularly the Dresselhaus effect in the field of spintronics. Jean worked alongside with Millie as they taught and inspired generations of students. Right before his passing, this late September, Jean was recognized with this year's American Physical Society Oliver E. Buckley Condensed Matter Physics Prize. This is considered as the world's most prestigious award in condensed matter physics. It's jointly awarded with Emmanuel Rashba for their groundbreaking work for pioneering research on spin-orbital coupling in crystals, particularly the foundational discovery of chiral spin-orbit interactions, which continue to enable new development in spin transport and topological materials. In 2008, Professor Mildred Dresselhaus was also awarded this prize. Although Millie and Jean worked together on many important topics, it is remarkable that they received this award on separate research works. It is humbling for us to walk in their footsteps. Thank you all.
Thank you, Jing. With that, I would like to invite Professor Vladimir Bulovich, Faribor's Massey Chair in Emerging Technology and Director of MIT.nano, to introduce today's speaker.
Thank you, Farnaz. Well, it's an honor to stand in front of you and indeed to relate this to a wide audience on the web. In honor of Millie, MIT.nano every November, right just about the time of Millie's birthday, that was November 11th, holds the Dresselhaus Lecture. This event recognizes a significant figure in science and engineering from anywhere in the world whose leadership and impact echo Millie's life, accomplishments, and values. And it's my distinct honor to recognize as 2021 Mildred S. Dresselhaus Lecturer, Professor Jelena Vučković. Professor Vučković is a Jensen Huang Professor in Global Leadership in the School of Engineering and Professor of Electrical Engineering by the courtesy also of Applied Physics at Stanford University, where she leads the nanoscale and quantum photonics group. She's also the chair of the Electrical Engineering Department at Stanford. She was the inaugural director of QFARM, the Stanford SLAC Quantum Science and Engineering Initiative, and is affiliated with Ginston Lab, Pulse Institute, Symes Institute, Stanford Photonics Research Center, SystemX Alliance, BioX, and Wutsai Neurosciences Institute at Stanford. Professor Vučković received her PhD at Caltech, California Institute of Technology, Yeah, after which she joined Stanford first as a postdoc and then continued her illustrious career at Stanford, where she is right now too. She has held additional visiting positions at Max Planck Institute for Quantum Optics in Munich, Germany, at the Institute for Advanced Studies of the Technical University of Munich, and the Institute for Physics of the Humboldt University in Berlin, Germany. She has, of course, received many, many awards for her during her distinguished career, including the James Gordon Memorial Speakership from the OSA, the ITAF Harvey Engineering Research Prize, Distinguished Scholar of the Max Planck Institute for Quantum Optics, Hans Fischer Senior Fellowship from the Institute for Advanced Studies in Munich, Humboldt Prize, Marko Jaric Award for Outstanding Achievement in Physics, and many, many others. It is my distinct honor to pass the floor to Professor Vučković. Thank you for being our lecturer today.
Thank you very much, Vladimir, for your kind introduction, to you and Farnaz and everybody else for inviting me to speak today. It's an immense honor to be selected as the Dresselhaus Lecture this year. It's also an immense pleasure to speak to all of you. I would like to start by saying a few words about how Mildred Dresselhaus inspired me. As you heard also from Jing just a moment ago, and as we all know, Mildred Dresselhaus was a giant of nanoscience, and she inspired everyone working in any area of nanoscience and beyond, including myself. And over the years, our paths crossed a couple of times, and I believe the last time I saw her was at the Munich Center for Nanoscale Summer School in Venice, Italy in 2010, where both of us were invited as speakers. And it was so inspiring to watch her interact with participants in the school, with all the students throughout the week of the summer school, because she was always surrounded by a group of people, by a group of students from school, and she would always answer all of their questions, not just about science, but also about career, about her career, give them career advice with the same energy, enthusiasm, and with her characteristic smile. Over the years, also, every time I would read any of her quotes or anything she said about being a woman, working between physics and engineering, being a mentor or being a mother, trying to navigate motherhood with mentoring and with scientific work, all of her quotes would resonate with me much more than quotes of other scientists I would read. So really, thank you, Millie, for inspiring and paving the way to the rest of us, because you showed us that it's possible to be a scientist, an amazing scientist, an amazing mentor, and also a mother. And I'd like to start my lecture with another quote, also by Millie, which has inspired my scientific work. If you don't have material, you don't have an experiment. So really, over the years, all of my research could be described with this quote. We always search for the next material that would enable the next experiment. And this journey started in grad school at Caltech for me, where I was doing experimental work on photonic crystals, which are these periodic structures that are used to control and manipulate the flow of light. And these periodic structures are really inspired by these natural crystals and carbon materials also that Millie herself was working on, except that you have some periodic arrangement of pillars or holes as opposed to periodic arrangement of atoms. And a lot of pioneering work on photonic crystals at that time in late 90s was done by the group of John Giannopoulos at MIT. And here I'm showing the cover of his really seminal book that he wrote with his former PhD student and another of your colleagues, Stephen Johnson and others. And here you see a silicon photonic crystal that was made by my group members a while back, where these periodic holes that we drill in silicon membranes kind of mimic these natural crystals. But in this case, we use them to control the flow of light, not really control the flow of electrons. But about 15 years ago, I started wondering whether this periodic arrangement of holes and patterns is the best way to manipulate light for a variety of applications. And this led me to work that I will be talking about today, where we really rely on computers and computer software to design the optimal structures to manipulate the flow of light. And that leads in some cases to these aperiodic patterns, non-intuitive patterns like the one behind me and on the screen, which end up working better than some of the regular and periodic patterns that we started with. So this work, this journey that I'll be talking about today started with the PhD thesis work of my former PhD student, Jessie Lu, who is also now back after a number of years in industry as a research scientist in my group. Jessie really wrote the first three-dimensional software for designing these structures actually in three-dimensional space. And then the next generation of students, we had really brought this to another level, including experimental demonstration, the first experimental demonstrations of these structures, Alex Pigot, Jan Petikiewicz, Logan Su, and then yet another generation of members, postdocs and students brought this to yet another level, both experimentally and computationally. Dries Verkruijsen, Niels Sapra, Raul Trivedi, Ginny Skarda, and Gun Ho An. And over the past few years, we started moving in the directions of practical applications and high density integration. And that's yet another generation of postdocs and students, Kiul Yang and Alex White, whom I'd like to acknowledge. And let me also use another of Millie's quote to summarize our journey. People said you're crazy, but if you think you're right, stick to it. And we were right. So let me tell you the story of how we came to where we are in terms of this research, where we now not only people who develop this software and who are specifically working on this particular type of research in my group are using this approach, but everybody else from my group also working on very different areas are relying on this. And also beyond our group in academia and industry, many researchers are pursuing this new approach in photonics. So let me take a step back and say what photonics is. Photonics is a branch of science and engineering, which studies guiding and manipulating light on a chip, as you see in these artistic renditions of photonic chips from industry. And there are many exciting applications of photonics today, and here I'm just highlighting some of them that my team members, my group is interested in at the moment. They range from optical interconnects, which are basically optical connections between different servers in data centers or between different chips or on chip, which reduces energy consumption and increases operating speed. Then variety of new optical computing platforms, including neuromorphic computing, new platforms for artificial intelligence, or even quantum computing platforms. Then augmented reality glasses, like the ones shown here, a variety of biosensors and imaging systems for medicine, including the one that I'm highlighting here, where I collaborated with some colleagues from Stanford on making real-time ELISA-type sensors. And finally, a variety of other sensors, including those for autonomous vehicles, like LiDAR, optical radar, which enables autonomous vehicles to move safely and scan their environment. But for all of these applications, kind of free space, traditional optical solutions would not really work, as the one on the left that you see in my lab, where we have a lot of components that we built into optical tables, because for pretty much all of these applications that I highlighted, you need to integrate a large number of optical components on the chip and fit that into footprint of your glasses or mobile devices or small sensors in the car. So the question is really whether we could go through the same revolution that electronics went through in 20th century, where from computing systems that occupy the whole buildings in mid-20th century, right now we have much more powerful computing systems inside of our mobile devices, where billions of components are integrated inside of a small chip. So can we do the same for photonics? Can we integrate millions or billions of components and enable these exciting applications and new functionalities? Unfortunately, photonics is not really yet at that level of integration, but we're hoping that we would get there with some of these exciting ideas that we and others are pursuing. So what is the problem with high density photonic integration? If we look at the state of the art or traditional photonic components, like the ones that we can order or ask commercial foundries to make for us on a chip, they're in general very large, tens of micrometers per component, much larger than electronic devices. And then they're also very sensitive to environment, fabrication errors, temperature variations, which is why people have to integrate all of these tuning elements like the ones you see here, heaters, in order to compensate for those environmental errors. Then they're designed by manual tuning of few parameters. There is a very limited library of photonic devices that people generally use. And there is no really reason to believe that many of them are optimal for particular applications. And also number of functionalities that we have are limited. So if you were interested in building some completely new functionality for photonics, there is no really library component for that, as I'll describe to you in a moment. As a result of this suboptimal process, a lot of these components are really inefficient. They're pretty lossy. Even in commercial systems, some of these couplers, for example, that foundries are making or people are using have 50% efficiency, meaning that you simply throw away 50% of the optical power before you even start processing signals on the chip. And that's not optimal for pretty much all the applications that I was mentioning. So the question is, how can we address this? How can we improve the way we design photonics so that we can eventually reach the level of integration that we have in electronics today? So here is our wish list. Can we achieve better device performance? Can we make photonics more compact? Can we make it robust to fabrication errors, temperature variations, so that we don't really need all of these complex tuning elements in addition to photonics on the chip? Can we implement new functionalities or eliminate this brute force design from the design process so that even electronics designers can design photonics? And we really believe that this is possible. And I will tell you about that process, new process that we and others are pursuing in photonics, which we call photonics inverse design, where we rely on sophisticated computational tools and modern computing platforms in order to find optimal photonic solutions, device designs for a particular function. And that's what we refer to as the inverse design. You start from how you would like your photonic block to operate, how it should map input to output with what efficiency and what footprint, and then computer software searches the whole parameter space of possible solutions for the one that is optimal, of course, within fabrication constraints. We design something that can be made. So in order to explain you what we're doing, let me take a step back and use a very simple example from photonics and show you how we would design that particular example, that particular component using this inverse design. So if you are making a photonic integrated chip, of course, you need some connections between components, which would be equivalent to wires on computer chips that we use to flow currents. But in this case, you have to flow light. You have to guide light between different pieces of a chip. And if you're connecting millions of components on a chip, you obviously have to make corners and turns at some points in these waveguides, in these guides that you're using for light. You can't really connect everything with straight lines. So how do you make a turn in order to enable high density of integration in these waveguides that are guiding light on a chip? Well, if you don't know anything about photonics, you may just say, well, I'll take up this waveguide, which may be a piece of silicon or a piece of glass, and just make a 90-degree turn as I would do in a regular wire guiding electrons. Unfortunately, it turns out that that's not an efficient way of solving this problem, because in the corner, you will lose around 3/4 of the power. So a few corners that you make, a few turns you make on a chip, and you lose all of the optical power. So this doesn't work. Then, intuitively, it may make sense to just round up that corner a bit, because even if you don't know anything about photonics, it may look like this sharp corner here is causing some trouble. So let's round this corner a bit and see what happens. It turns out that this indeed is a better solution, but not really 100% efficient. You will still lose around 17% of the power at that corner. So again, few turns and a lot of power is lost. How do you solve this in a better way? Well, then, you can say, well, I make a smooth turn, right? I make a much larger radius of curvature turn here. Instead of 2 micrometer radius in silicon, let's make a 10 micrometer radius in silicon, or something like 50 micrometer radius in silicon nitride. And indeed, if you do that, if you make this large radius of curvature turn for your waveguide, you will make it nearly 100% efficient. You will not really lose any power in this corner. But then that makes a problem with the high density integration, because if you need tens of micrometers for each corner, for each waveguide band, you will not really be able to integrate millions or billions of components on a small chip. So is there a solution that enables us to make this turn with 100% efficiency, but in a smaller footprint? So in order to address this problem, we can rely on inverse design. Rely on this software that searches all possible solutions for the geometry of this corner and tries to find a solution that will really bend the light with 100% efficiency, but in a much smaller footprint. And if you let the computer software search all possible geometries, all possible kind of patterns in a piece of silicon that it's in that corner, this is what it would find as an optimal solution. And this optimal solution is also 100% efficient, but is much smaller than the way people would traditionally band these waveguides with very large radius of curvature. It would fit inside of this small square as opposed to this large band that you see in the picture. And if you actually look at how electromagnetic field propagates through this corner, you will see that it's banding here with kind of nearly 100% efficiencies. You are not really losing much in that corner. So clearly, there are solutions out there that are equally efficient and either have small footprint or are more efficient than traditional solutions, but we have to find them, right? Because the space of all possible geometries is really rich and enormous. So how do we do that? Let's look at another problem, which people also have to often address in photonics, where you're converting pattern of optical field between input and output. Let's say at the input, we have some optical field with one lobe, as shown here, and at the output, you would have two lobes, positive and negative, as shown here. So how would you do this? Normally in traditional photonics, people will do adiabatic mode conversion, where they slowly expand this guide over hundreds of micrometers of the footprint on the chip so that they can convert from this input to this output with nearly 100% efficiency. But that is hundreds of micrometers, again, a lot of real estate. So the question is, can you do this in a much smaller footprint with the same efficiency? Can you do it in a 2.5 by 1.5 micrometer footprint, many orders of magnitude smaller, but with greater than 90% efficiency? Well, in order to check whether that's possible, we can say, well, let's pixelate this into 100 nanometer pixels of silicon, and let's try all possible combinations of silicon and air here and find the pattern that potentially converts between input and output, if there is such a solution. The problem is that even for such a tiny structure and big pixels, the number of possibilities and the number of possible patterns that you have there is 10 to the power of 112, which is larger than the number of atoms in the observable universe. So unless you're extremely lucky in your lifetime, you will not really be able to analyze all of these structures and see which one works as a mode converter. But the message is that this parameter space is enormous. So you have to go through all of this space somehow in a more efficient manner. And the way to travel through it is using physics-guided searches, travel guided by the physics of the problem. And here is what we actually do. It's the same footprint. And here you can see on the left, the movie of how you travel through that enormous parameter space driven by the physics of the problem using optimization tools and techniques, which are basically just multidimensional versions of very simple gradient descent techniques that I'm sure many of you have seen in math classes. And on the right, you see how optical field, solution of electromagnetic field, optical field for this structure changes as you're traveling through that parameter space. And here is a little bit of more analysis until you converge to something that you can make, because of course it's important to find a solution that is also fabricable. And you stop when you reach the target efficiency here greater than 90%, you find the pattern that you can make, and it converts the field in the matter you like. And although I'm showing you just these two-dimensional cross-section of the field here. All of this design is done in 3 dimensions because you have to capture the structure completely in order to capture its loss and behavior and so on. So the full optimization of this device, which takes several hundred iterations, takes about 1 hour on gaming GPUs. So we don't really use supercomputers, we just use gaming GPUs here in the process that cost few $1,000s, and we can run thousands of these simulations within an hour, which means that both fast optimization tool and fast electromagnetic solvers are very important to solve this problem. Let's look at another problem here where we would like to build a very compact structure that splits 2 different colors of light, 2 different wavelengths, and in a very compact footprint. Normally, people would do this in a footprint that is at least 10 by 10 micrometers in size. Here, we would like to do it in 2.5 by 2.5 micrometers. So if you search for the optimal structure, the optimal geometry that would do this, here is how the search through the parameter space would look like. So you see the software searching for the optimal solution that would do this mapping. And what is actually also very interesting here is that even if you constrain the footprint to something that's at least an order of magnitude smaller than traditional solutions, in that tiny footprint, we could find 6 solutions that are equally efficient. You see one of them on the screen, and you see another one behind me. And they were both equally efficient in terms of splitting these 2 different colors of light. So we decided to make the one that I'm showing you here on the slide, and which is also featured behind me. The design is in the top right corner, and the fabricated device is here on the left and bottom. This is drilled holes in the piece of silicon, which are supposed to split these 2 different colors of light in an efficient manner, greater than 90% efficiency. And if you scan the input wavelength, the input color of light, you see that first you're transmitting to the top port, and then you're transmitting to the bottom port as desired. And if you make a lot of these structures and measure all of them, they would all perform the same as shown here in the transmission plot. So this is the transmission for many devices on the chip that are plotted at the same time. And what is important is that we don't do any tuning or tweaking of the parameters after the fabrication. Although our fabrication is not perfect, they all perform the same because we incorporated robustness to typical fabrication errors into the design process. And then we could actually extend this to splitting even more than 2 colors of light. For example, 3 colors of light at the bottom in a slightly bigger footprint, 4 by 5 micrometers. And again, post-fabrication, we don't do any tuning of the structures. We measure them and they all perform the same. These are transmission plots plotted on top of each other. So we started with these initial designs of mode converters and wavelength splitters in a more compact manner and robust to fabrication errors and to environmental conditions to prove that this approach really works. But our initial experimental attempts were all constrained to our fabrication facility at Stanford Nano Fabrication Facility and electron beam lithography and kind of, university experimental fabrication tools. But over the past 5 years, we wanted to go beyond that. First, we wanted to show that we can also use this approach to design new functionalities that don't exist in photonics. So not just to shrink existing functionalities or make them more robust, but also to do new things. And I'll explain that in the example of the ultimately new functionality for photonics, which is high energy physics, making particle accelerator on a chip. And we also wanted to show that we can translate this approach to high throughput fabrication in a foundry, in a commercial foundry, because if we were to integrate millions or billions of components, we certainly have to rely on commercial foundries in that process. And since we've been working on this for a long time, we also developed a software suite, which we called SPINS, Stanford Photonics Inverse Design Software, which many people are using right now beyond our group. There is a basic version, SPINS-B, which is open source, and you can download it from our GitHub webpage and play yourself and design some photonic devices, or you can also license the full version from Stanford. So let me describe what we do also in terms of discovering and enabling new functionalities in, again, the example of ultimately new maybe functionality for photonics, which is high energy physics, particle accelerator. So when we mention particle accelerator, all of us think about these gigantic structures that occupy miles of space. For example, Stanford Linear Accelerator, SLAC, is few miles long, sits next to Stanford, or LHC at CERN is also a gigantic facility. But as we all know, these accelerators only exist at few places around the world, and people have to travel there in order to do their experiments. Of course, there are also other types of accelerators, lower energy ones, not as high energy as the state-of-the-art accelerators for high energy physics, but still pretty large and not accessible everywhere. Those are mega electron volt accelerators that are used in medical facilities for radiation treatment, for example. And they also occupy the whole rooms and are pretty expensive because they also have to accelerate particles to large energies. As we know, because of this size and cost, they're not really accessible at every medical facility around the corner. So people, you would usually have to travel for treatment to specialized facilities. So the question is, can we do something about this? Can we make these accelerators more accessible, cheaper, or smaller in size and scale, so that people can actually kind of have accelerator in their own facility, in their own lab, or every medical facility around the corner? And this work is really inspired by ideas of my colleague Bob Beyer, who has been thinking about this for decades. And it's really a very simple idea. State-of-the-art accelerators use microwaves or radio frequency waves to accelerate particles. But these waves have wavelength separation between crests of electromagnetic waves that are about 10,000 times larger than for optical waves. So if we could use different spectrum of electromagnetic waves, shorter wavelengths to do the same function of accelerating particles, we should in principle be able to shrink the size of accelerator. So SLAC, which is few miles long, could be shrunk to 1 inch on a wafer if we just replace electromagnetic fields used for acceleration from microwave and radio frequency waves with optical waves. But this problem is not trivial. You can't just take accelerator and shrink everything by a factor of 10,000 because building blocks would not really work for optical waves. So you have to redesign everything in such a way that components are working for optical fields. And this is really new functionality in photonics because we don't really have off-the-shelf components that we could use to accelerate particles, couple of optical fields and use them to accelerate particles. And this is why we decided to use inverse design in this process in order to design these new building blocks. And here you see how design process looks like. Our software is searching through parameter space to find something that would really, for coupled optical field, accelerate electrons that propagate through this vacuum channel with some initial energy. And these electrons would always be accelerated. They would always provide kick in the right direction. They would never be decelerated. And the pattern that we have to make in the structure is shown on top, and the electromagnetic field distribution is shown on the bottom. So once you design the structure, you can make it. Here it is, made in the piece of silicon. And for the couple optical field at the infrared wavelengths of 2 micrometers, here's how the field pattern would look like. So for incoming electron going here, it's always accelerated. It never really receives it always provides the kick in the right direction. So again, once you have the whole system, the whole design, you can build the system. Here is the stage of the accelerator, which is 30 micrometers long. Here is the coupler, which is also designed in such a way that it can couple these energetic, very short pulses for the laser without damaging and burning the structure. And what you do in the actual system is you couple laser, you propagate, you have the stage of accelerator here, all in silicon, and you measure performance. And keep in mind that this is just a single stage of accelerator. Even in traditional accelerators, you would have a lot of stages, and each one would accelerate particles more and more until you reach the target energies. So what we did here so far is just a single stage, but in the actual system, there would be hundreds or thousands of these stacked together on the same silicon chip, which is certainly possible because each stage takes only 30 micrometers. So this is a 10,000-fold reduction in size, but when we characterize it and measure, we actually see acceleration gradient of 30 megaelectron volts per meter, meaning that an electron propagating through this structure would get energy of 30 megaelectron volts per meter of length. And within an inch, we could go from the input energy of 80 kilo electron volts to mega electron volt, which is already very useful for medicine. So here is the experiment, the whole chip. When we couple electrons from converted scanning electron microscope with energy of 83.4 kilo electron volts, if the laser is off, they just exit with the same energy. If the laser is on, they just get the kick of 1 kilo electron volt per 30 micrometers. And they're accelerated with this target acceleration gradient. So if you put 100 or 1,000 of these, by the time they exit this inch of a chip, they would have energy of mega electron volt, and that could already be very useful for a variety of applications. And that's what we're working on right now. But of course, we don't want to go to integration level of thousands of stages and do that in our university facility. We're working with commercial foundries on integration of large number of stages so that we could actually build practical accelerator and maybe shrink slack from few miles onto an inch of the wafer. So yet another exciting application that I'd like to share with you, just to give you state of the art of how we can actually use this in practical environments, is this optical interconnects. I mentioned previously that optical interconnects are optical connections between computers in data centers or between different chips on the same computer or even on the same chip. And the idea in replacing electronic connections with optics is because it could reduce energy consumption, but increase the operating speed of all of these systems. And this is already done, of course, in data centers between different servers, but the idea is also to deploy it at the chip level or between different chips for the same reason. And a lot of people are working on this, and there is a lot of excitement in this problem, but there are also a variety of bottlenecks. The question is, how do you increase the number of channels? How do you maximize the communication rate with minimal error rates and minimal loss so that you can really deploy this in practical environment? And by relying on this inverse design and inverse design elements, we were recently able, in collaboration with our colleagues, to get to very large communication rates, terabit per second, which is 10 to 12 bits communicated every second between different chips or on the same chip, and with negligible bit error rates. Only 1 bit was flipped every second per every 10 to 12 bits that were communicated. And this was, of course, done in a commercial foundry, in a fabrication facility in a commercial foundry, because that's very important in order to deploy this in practical environments. This is how the whole system looks like. And we are maximizing the number of channels that we're communicating here by introducing another dimension. Instead of just using different colors of light to communicate in different channels, we're just also using different spatial patterns for light so that we multiplicatively increase the number of channels beyond what people would normally do. And the enabling element here is this component, which is also inverse designed, and it kind of looks like the thing you see behind me. There's some subtle differences in the pattern. It's also few by few microns in size, but the function is very different. So what this does is it takes the optical input from each of these input channels and converts it to different spatial mode at the output. So you see here 1 lobe or 2 lobes or 3 lobes or 4 lobes at the output. And it does that with very high efficiency, and it does it for many, many different colors of light so that you can still use color of light as another dimension for increasing the communication speed. And when you build this and measure the communication speed, you can really communicate at very high rates with minimal bit errors, as all of these diagrams actually are here showing. So again, you can do even practical functionalities and foundry-based fabrication and new functionalities by relying on this design, by relying on computer to design something for you. Yet another kind of interesting application that I mentioned in the initial applications of our and others' interests are these LiDARs for autonomous vehicles, right? So how do you build this system that would scan the environment in a very efficient way and have a computer inside of your car that would make decisions for you? And of course, there are many companies working on this, and this movie is from Waymo. And if you've seen some of these LiDAR systems and self-driving cars around, they have these gigantic things sitting on top of the car, which is actually a LiDAR system that has all the mechanics that enables rotation of these beams and enables the scanning of the environment, which is the key element for enabling this autonomous driving. But the question that we would like to answer is whether you really need these gigantic things sitting on top of the car, which is at the same time really expensive. It costs several tens of thousands of dollars. Can you make this system inside of a footprint of a single chip, which would be just like another sensor in your car? And can it be inexpensive? Can it cost less than $100? And we started looking into different elements of this and different functions. And one of the things they need to address in this process is, can you steer the beam somehow with all of these mechanical components? And can you do it with inexpensive lasers so that you can enable scanning of the environment? And if we let computer kind of search all possible solutions for the best structure that would enable you scanning, kind of steering the beam at the output when you only scan the input color of light, this is how the structure would look like. So there are all these different elements that almost look like errors in fabrication, but they're actually optimal pattern within fabrication constraints of our process. And this enables steering of the beam by 20 degrees when you tune input wavelength by 20 nanometers, which requires much less expensive laser than the previous state of the art, where you could steer the beam by 15 degrees if you tune the laser by 100 nanometers. And once you make all of this, and tested, here is your beam steering by 20 degrees for input tuning of 20 nanometers. So the point of this is there are so many solutions out there, and we never really used them or looked into them until we started searching through all of these complicated parameter spaces using these efficient methods and relying on modern computational tools and hardware platforms. And even if you shrink the footprint by orders of magnitude, there are multiple solutions that are equally efficient as the traditional ones, or new functionalities that we have not even been aware of. So as an example of yet another functionality, exciting functionality, I'd like to spend a few moments telling you a little bit about quantum technologies, because there is a lot of interest and excitement around quantum technologies these days. And you may have seen news releases from major companies like IBM and Google regarding superconducting quantum processors consisting of several dozens of qubits, quantum bits, or atomic quantum simulators like the one featured here from the group of Emanuel Bloch in Munich. But of course, there is a lot of beautiful work at MIT in the group of Vladan Vuletic and others on the same types of systems that have a few hundreds of atoms that are used to simulate some other quantum processes, which is not really reachable on classical computers. Or what we are trying to do actually in my group at Stanford is kind of shrink this onto the footprint of a single chip, single diamond chip or silicon carbide chip, and simplify a lot of this infrastructure, but also hopefully enable larger scaling of these systems to even scale beyond few hundreds of qubits where we are now, and can we really rely on all of the semiconductor processing and in this process and scale it to even larger and even more useful scales. So that's really what we're doing. And we are really at the moment focusing on two materials, diamond and silicon carbide, and relying on some impurities in these materials as our quantum bits that we're optically controlling. And if you listen to last year's Dresselhaus Lecture, beautiful lecture by my colleague Evelyn Hu from Harvard, she talked exactly about that, about these impurities in diamond and silicon carbide, which in high concentrations lead to colors of these materials, for example, for jewelry, but in low concentrations are very useful for these quantum applications, practical applications. So I will not really go into details of these qubits and their operation, just say a few words for those of you who may not be familiar with them. Really, our quantum bit is this individual impurity defect inside of the material. For example, here you see tin impurity, extra thin atom embedded inside of diamond. But likewise, you can have silicon in diamond, or you can have some missing silicon atoms in silicon carbide. And this is really like naturally trapped atom or ion inside of this solid. It's kind of the same as atomic physics experiments, but you don't really need trap to trap atom or ion. It's already trapped by the lattice. Of course, that leads to interaction with the environment. So you have to make sure that you minimize defects and minimize that interaction, because it's not really a vacuum, but physically it is the same platform. And physically it's also the same as superconducting qubit in a microwave cavity, except that we have these optical transitions inside of our artificial atom, and it's coupled to an optical cavity. Of course, you have to deal with all of these potential defects and interaction with the environment and suppress it as much as possible. And you have to build everything that is on the scales that are about 1,000 times smaller than for these superconducting qubits that operate at microwave wavelengths. And that's, of course, much harder. But on the brighter note, you work with semiconductors, you can operate at a little bit higher temperatures. You already have excellent optical interfaces, which is great for building quantum networks. And you can actually even do more operations before the system loses quantum mechanical properties than in some of the other leading systems. So towards this effort, we've been working on a variety of material developments and fabrication techniques that allow us to put these atoms at desired positions, trap them there with minimal defects. And what we really do is we mask materials, we implant them inside of the material at low energy to minimize damage, and then we regrow material on top, and we can actually implant them wherever we like. And you heard more from Evelyn last year about all the details of these exciting developments and experiments. But I'd like to focus on, again, the photonics side of things, because just implanting them there is not enough. You still need light and photons to connect all of these different quantum bits and build entangled states and use them for some more exciting applications in quantum networking and quantum computing. So how do you build photonics in these non-traditional photonics materials like diamond and silicon carbide? Most of photonics that you see today, and pretty much everything that I talked about today in my talk so far, was in silicon, right? And silicon is a great material for electronics and also for photonics, because 20 years ago, thin films of silicon on insulator were commercialized, and you always need this thin layer of some high index material that you could use to guide light. And since that became available 20 years ago, and since silicon is also a material that is actually easy to process in commercial foundries, most of silicon or photonics effort is actually focused on silicon. And likewise, about 10 years ago, another photonic material was commercialized. That's thin film lithium niobate on insulator. And over the past 10 years, those of you working on photonics may have seen a lot of exciting developments in this particular material. But diamond and silicon carbide are not photonic materials. We don't really have thin film diamond on insulator or thin film silicon carbide on insulator that we could use to carve out photonics, which is why we have to basically figure out how to do it ourselves. How do we make this guiding layer and carve out photonic structures inside of the material? So for diamond, we're doing something that was originally pioneered by Paul Barkley at the University of Calgary, and also further developed by Dirk Englund at MIT, which is three-dimensional bulk carving. We take a piece of diamond and we literally carve it down and sideways, and we can combine it with these non-intuitive designs. We can also combine it with computers, letting computers search through the whole parameter space of solutions until we find the ones that work. So that really works nicely, and it can also work without impacting properties of these impurities, these trapped thin atoms inside of the material, which we can still use for qubits. So here you see example of a resonator with some optimized structures at the end, and there is a single thin impurity embedded inside of the structure, and we can use this whole system to enhance its coupling to photons and then connect it to some of the other impurities on the chip and off the chip and use it for practical applications. And in silicon carbide, it's the same story. Silicon carbide is much less expensive than diamond, and you may know that people use it to make fake diamonds. It's also used for power electronics. It's used for heating elements, for abrasives. It's used for sanding paper. And you can get it on 6-inch substrates. It became commercially available 30 years ago, but you don't really have thin film silicon carbide on insulator that you can use to make photonics. This is how silicon carbide generally looks like, and how do you turn that into photonics that could even host some quantum centers and have some interesting properties for building photonic or quantum systems. So what we do is we take a piece of silicon carbide, we bond it onto some piece of glass, and we grind it and tin it and polish it, and it doesn't look like a sophisticated effort, but it leads to a thin film, few hundred nanometers, that can guide light, and then we can fabricate and make all of our sophisticated structures inside of it. So we really go from this to something like this. And once we have a thin film on the substrate, we can fabricate photonics inside of it. And here is the final product. And again, you see these computer-generated designs and some circles that act as resonators. And here are more of those. And in the process, you end up with very high quality structures, and you can combine it with the optimal behavior for a particular function. And you can even use this to build sources for both optical interconnects or for quantum applications. And here is one example of that, where we use the piece of silicon carbide to generate what is called frequency comb, which is this spectrum of colors of light that are separated by equal amount. So it looks really like teeth in the comb, but we can do it just in a piece of silicon carbide. And then if this is already useful for optical interconnects or for metrology or for sensing, but then if you look deeper below this initial set of teeth in a comb, if you look below the noise level that we would normally not analyze, we see another set of teeth that are even more useful for quantum applications. So let me kind of close my talk by saying that, and addressing the question posed in the title of my talk, are computers better than humans in designing photonics? Well, based on our experience over the past 15 years, we do believe that that is really the case. That for many applications, letting computer software search for optimal solution leads to much better solutions than what you would design or guess based on your intuition. And this process is material agnostic. It's fully compatible with commercial foundries. It also enables new functionalities. And I feel that we've just touched the tip of an iceberg. There is so much richness and so much space in this parameter space of possible solutions that you can fabricate, that, you know, even when we try to make something a little bit better than the traditional solution, just smaller in a footprint or higher in efficiency, we can come up with multiple solutions that are equally good or even better than what we knew before. So I feel like we are relearning photonics and electromagnetics in this process. And of course, computers are not doing this on their own. They're programmed by researchers and experts, and we're riding the wave of the recent developments in computer hardware and also in software in enabling this effort. And let me just close by thanking all of my group members, present and past, in enabling where we are today, and also our funding. And thank you all for your attention.
Thank you, Jelena. It is truly an inspiring talk that spans many aspects of an opportunity in in photonics in general. Silicon carbide, diamond, many others. I would like to then go ahead and get us started by asking some fairly straightforward questions and then ask for additional ones from the audience to be joined in. The very first question I have is to get a good sense of how much intuition can be developed from all the insights that computers do provide us. You mentioned in your concluding statements that indeed the computers can provide us fantastic amount of insights, but can those develop in us some rules of thumb to follow next time around, maybe shortening that, was it 10 to the 112th combinations that are available, to maybe just a few that we should start with, and then let computers optimize them?
Yes, yeah, that's a great question, Vladimir, and that's, we're actually learning, as I said at the very end, we're relearning photonics in the process and developing new intuition on how to design devices. And We learned some things along the way. We're also trying to make some analytical kind of bounds on the problems that we're solving. And also there is a new community of researchers developing around that. What are the bounds on design? What is the minimum footprint that you would need for a particular function? What is the best part of parameter space to look into? How do you converge there faster than you normally would? We have some intuition developed on how we initialize the process so that we converge the solution that is fabricable, right, or more robust to the errors, or what footprint you need for a particular role. But again, it's just the tip of an iceberg. I think there is so much more to learn and so much more to see in the process. So what we focused so far is enabling this search in a most efficient way, right? Making better electromagnetic solvers, using better optimizers. But hopefully down the road in the future, we will also, the computer itself, using some analytical bounds that maybe we develop, will be able to tell us, instead of going through trial and error, what is the best way to start and where to look for solution instead of looking everywhere in this gigantic space.
Yeah, well, which of course, every time that we design things on computer, we expect perfection of the design, meaning the edges of the waveguide or of the etched features have no defects, and consequently, the result is always perfect, or hoping that it actually gets there. Is there a way to evaluate the tolerances of the designs, meaning how much error will you implement in the process?
Yeah, so we do that. Yeah, absolutely. So we do that routinely in our design. We incorporate fabrication constraints. And when we started doing this, we didn't really do that. We would just search everywhere and we wouldn't really constrain the process. But of course, as experimentalists, being able to make things is most important for us, right? Having material for our experiment, to quote Mildred Dresselhaus. So what we do is we do incorporate our typical fabrication constraints. And for example, for the process that we can run ourselves at Stanford in nanofabrication facility, minimum features that we can make reliably are 80 nanometers for something that we etch through piece of silicon completely. You were talking about something like partial etches, then there is etch lag. Small features don't etch as fast as big features. Those of you doing fabrication know all about this volt profile and all the other things that you can also incorporate in the process. And then when you switch material, even if you use the same facility, for example, diamond, we can't really process diamond as well as silicon. Features are bigger. Or when you use commercial foundry, they have their own set of rules, right, which you also have to incorporate into your design. So what we do is whenever we change the process or material, we have to characterize the rules, characterize the process, or get the rules, design rules from a foundry. And we take those design rules in the process of optimization, and we use this to constrain optimization so that when the software kind of searches through this whole parameter space, it rejects the solution that would not satisfy these constraints and design rules.
I assume that although you've shown us single devices, systems in a similar fashion could be simply cascaded by cascading different devices.
Oh, yeah, absolutely. So what we're now able to do is design things in 3 dimensions that are maybe up to 10 to 20 micrometers in linear dimension. And of course, the larger the structure you have, the larger the problem you have to solve. So if you're doing even single electromagnetic simulation, you know that it takes more time to run simulation, and we need to run thousands of them in series. And you don't want to have a design tool where you need to wait month to get to the optimal solution, or see that after a month that there is no optimal solution. So what we're trying to do now is really speed up these solvers so that even for much larger structures, or maybe like the whole system, something that's 100 micrometers in size, you can design it in a reasonable amount of time. But certainly, as you said, what we can do now is design individual blocks and cascade them. And that works fine for a lot of things that we do, I mean, as I was describing today. But in some cases, you really need large footprint, right? If you were to go from just splitting 2 colors to splitting 100 colors in a single block without cascading, you will need a larger footprint. And that's beyond the reach of what we can design now.
It is very exciting to consider the 3-dimensional designs that you're starting to look into. But let me ask you, I'm noticing your LiDAR design. You indeed are able to steer the beam over 20 degrees, if I recall properly, by changing the color ever so slightly of the incoming light. Beyond this passive way of steering, call it by changing the color, is there an effort in looking at modulators or indeed changing this industry refraction or the shapes of the designs? And how would you do that?
Yes, so that indeed is something that we do for other applications and for LiDAR type application and switching applications. And that's completely doable with the current approach, because whenever you're doing some sort of modulation or active design, in most cases, unless you're doing some micromechanical structures, you're not really changing geometry of your system. You're just doing something that will change index of refraction, right? How fast light propagates through the material, which means that the problem of optimization is still problem of designing geometry, but designing geometry for different indices of refraction so that it performs different function when you have one index versus the other index that you change using something like free carrier injection or some nonlinear process. And we do that. I mean, it is computationally the same as optimization for multiple inputs or for multiple colors. It's just mathematically of the same complexity, but it's still searching for the optimal geometry that works for different indices. And on the comment regarding three-dimensional designs, I should mention that everything that we do is actually three-dimensional design, but we constrain geometry to a single pattern in a slab because that's something that we can easily make. Although recently we started working on two-dimensional kind of arbitrary patterns that are aligned, which we can make in a commercial foundry. So it's not a matter of not being able to design them, it's an issue with fabrication. And complex three-dimensional fabrication is beyond the reach of what my group is doing at least. And in commercial foundries, maybe you can do a few layers that are aligned to each other.
So it sounds like integrated microelectronics is coming to a chip near you.
With photonics, yes. Hopefully, yes, that's what we hope. Yeah.
So are you? And what would be, call it, the estimate at what point the foundries will take this as a norm to integrate photonics onto their chips?
Yes, so that's actually really interesting. We've worked with all the major commercial foundries in implementing this and doing this, and we started this and did the first experimental demonstrations using Stanford fabrication facility, like the thing you see behind me. Then at that time, when people from a foundry would see this, it looked like a nightmare, right? They don't like to see these irregular patterns and, how do you design this? This is probably not going to work. But then we slowly started working with everyone, initially with global foundries and then AIM Photonics. And then recently we worked with Advanced Micro Foundries and IMEC. I mean, pretty much all of kind of major foundries working on photonics and implemented devices in all of them within their fabrication constraints successfully. And initially there is always an element of surprise, when people see design, its first reaction is, no, this will never work better than, circle, right? Or, some kind of slowly expanding structure, something that is geometrically kind of almost perfect, right? But then when people see how it works, then they become more open to incorporating it into maybe even their offerings or their chips. And we're working with them on, including some of these structures, maybe eventually into PDK, their toolkit that people can access externally when they're actually sending their chips for fabrication.
Well, Jelena, thank you so much for a fantastic lecture, for so many insights you have provided us. There are many, many more questions, and indeed, you might have a chance to ask them after the lecture in a less formal fashion when we reconnect with Jelena right after the Dresselhaus Lecture finishes. But to finish off the lecture, I would ask my colleague, Professor Farnaz Nirui, to join me and indeed tell us just a few parting words.
Thank you. Thanks, Vladimir. Thanks, Jelena, for a wonderful talk. Very inspiring. We have a very small memento as just a token of our appreciation. It's handmade here at MIT's own glass lab, which we'll send to you soon. Thank you again very much for your wonderful talk.
Thank you very much, Farnaz and Vladimir. It's been my honor. Thank you. Hope
Thanks.
to see you all soon in person.
Thanks, hopefully.
Thank you.